So we're going to look at some additional graphs of functions and relations in this, and we're starting chapter 9. So first we're going to review the operations we can do with fractions. Remember, operations are addition, subtraction, multiplication, division, those types of things. Then we're going to find a difference quotient, and we're going to work on composite functions. So composite functions are going to be functions that are like nesting dolls. If you've seen the German nesting dolls, it's like you're putting one inside of another. So let's review some operations. What can we do with functions? We can add them, we can subtract them, we can multiply them, or we can divide them. So I can do 3x plus 2x. I can do 2x minus 5. So this looks really complicated, but what is happening in the parentheses is it's telling you the operation to do on the two equations. So if I have the equation 2x plus 1 and x minus 5, this is telling me to add them together and then plug in 1. So I can do this by taking the f of 1 plus the g of 1 and adding those together. So some students prefer to say, okay, 2x plus x is 3x, 1 plus negative 5 is this value, so I add those together. This is just a little bit easier where we're going to plug 1 in to the first equation, plus we're going to plug 1 into the second equation, and then we're going to get our final answer. Same thing happens in part B. It wants me to subtract, but plug in negative 2. So I'm going to plug negative 2 in for x, and it's really important, guys, that you plug in parentheses. Very, very important. And that you make sure and use the minus the whole quantity of g of x. So I want to subtract this whole number here. So I get negative 3 minus negative 7, which is actually going to give me positive 4. In C, the two letters written next to each other is going to imply multiplication. So I want to plug 1 in to both of them and then multiply them. Again, if it's not negative, we're not necessarily huge in the parentheses, but it's a good best practice. So I get negative 12. And then in D, this is a fraction, but it's indicating division. So I'm going to plug 7 in to both of them. Then I'm going to divide them, and I'm going to get 15 over 2. And it's okay to have a fractional value of 15 over 2. That's fine. So let's look at a few more. What happens when we don't want to plug in a value? Here, it's remaining as x. I'm not plugging anything in, so I'm straight adding the two equations, and then I'm combining like terms. 4 minus 3 is the only like term here, so I get this quadratic. In any polynomial, the domain is always all real numbers. So unless you're being divided by something, you have the square root of something, you are going to be all real numbers. In part B, it wants me to subtract them, but I'm not plugging anything in. I use parentheses so that I remember to distribute that subtraction symbol through both terms. I have a quadratic, so that's a polynomial, and the domain is always going to be all real numbers. In C, I want to multiply the two equations together. This is going to require the use of FOIL, or a distribution property. We're going to do 3 times x squared would be 3x cubed. 3x times negative 3 would be negative 9x. 4 times x squared is 4x squared, and 4 times negative 3 is negative 12. In D, I want to divide them. So that's the first place where I might have a domain that's not all real numbers, because I'm doing some division here. When you divide them, the majority of the time, you're not really going to be able to simplify them very much, but where the denominator equals 0 will be where we have a problem with our domain. So when I do this, I'm going to take the square root of both sides, and my square root's not popping up. So this is actually the plus or minus the square root of 3, and that's where my domain is coming from. I'm going from negative infinity, I'm taking a stop here, picking back up, stopping, picking back up, and going to infinity. So when I'm working with the domains of these values, they include all real numbers that are in both of the domains f and g. The domain of those real numbers in the intersections would be for where g of x is not 0 when you're dividing the two. So what this is saying is, if you divide two polynomials, you've got to watch out for where it equals 0 in the denominator. If you're just adding, subtracting, or multiplying, then we don't really have to worry about that because we don't have a problem with the domain. So this is called a difference quotient, and this is really important in the study of calculus, but it's also a great exercise in honing in those algebra skills that are going to be needed in a lot of different professions. So what we're going to do is we're going to replace x with x plus h. Then we're going to subtract the original equation, and we're going to divide it by h. So if I do f of x plus h, I'm going to need to FOIL that out. And then I'm going to need to distribute the 3. So this is this whole piece right here. Now I'm going to subtract my original equation from it. So see that? Minus the original equation. And I'm going to have some cancellations because I have 3x squared minus 3x squared. Well, those are going to cancel. I have minus 1 minus negative 1. So those are going to cancel. Notice that each term here has an h. So I'm going to go ahead and do that division by factoring the h out and canceling it. Then I'm going to get 6x plus 3h. Here's Miss Robinson's tip. If every term is not canceling out that does not have an h, you did something wrong. Every term without an h should cancel, always. You should always be able to factor out an h and then cancel it with the denominator. That's very important. That is how you self-check your work and figure out if you've made an error somewhere. So now we're going to look at composite functions, and that's that whole nesting doll idea where you have the big doll, the smaller doll, and you keep opening them up to finding more dolls. The first problem that we encounter with composition functions as teachers is students want to multiply them. So they see this open circle, and a lot of times we use that closed circle to indicate multiplication. But this is not multiplication. This actually means put g of x inside of f of x. Do you see that? G of x is inside f of x. So that's what it's telling me to do. And the domain of this value, or this equation, is going to be the set of all numbers that are in the domain of g, but also in the domain of f. What does this look like? So let's first look at it with numbers, because when we look at things with numbers, it's always so much easier. So this means to plug 3 into the g equation. So I'm going to replace x with 3, and I get 2 over 3. Now, instead of g of 3, this becomes f of 2 over 3. I'm going to replace x in my f equation with 2 over 3 so that the 3's are going to cancel out, and I'm going to get 2 plus 2, which is 4. So there's multiple steps that happen here. You've got to plug it into g, take that answer out, and plug it into f. Let's look at it again. I'm doing it the other way around now. Now I'm going to plug 3 into my f value. Then I'm going to take that 11 and plug it into my g value. So the order that things are happening in those parentheses is important because it's either plugging into f or plugging into g. That's how you're going to tell. Now we're going to do it without numbers. So this means to put g of x inside of f of x. So everywhere there's an x, I'm going to write 1 minus 4x. I do that in parentheses because that's a best practice. So instead of an x squared, it's 1 minus 4x squared, which is going to require me to FOIL. Once I complete the FOIL, this is what I have. I'm going to combine my like terms of 1 and 3, and I get this. Now the lab isn't necessarily going to specify the order these terms are written in, but it's a best practice to write the highest exponent first and then write it in what we call descending order. When I look at the domain of this, it's a polynomial. It's all polynomials. The domain of all polynomials is negative infinity to positive infinity. Now I want to take and put f of x inside of g of x. So that's a typo. That should be g and f of x. I apologize. So now we're going to take f of x, x squared plus 3, and replace it here for x. Okay, did you see that? I'm replacing x with x squared plus 3. Then I'm going to combine my like terms, and it's a polynomial, so my domain is going to be all real numbers. Let's try it again. I want to put g of x inside of f of x. So instead of x cubed, it's going to be 4x cubed. I cube 4, I get 64. I cube 3, I get x cubed. It's a polynomial. That's my domain. Let's do it backwards. Now I'm going to put f of x inside of g of x. So instead of x, I'm going to write x cubed plus 2, or negative x cubed plus 2. I put it inside, I distribute the 4, goes to both terms, and it's a polynomial, so my domain is all real numbers. Now we have a square root, so now we're going to get into something a little trickier with domain. So I want to take g of x and put it inside of f of x. That's what this is telling me to do. It says we could substitute 2x for the x in the radical, because I want to find the functions f and g. So this is my composite function. I've placed g of x inside of f of x. So that is one possible solution, that I have x plus 3, and I'm replacing x with 2x. Possible. Or it could be 2x plus 3 and that g of x just equals x. So there might be more than one answer, which is why we're not going to see a whole lot of this type of question in the lab, but it is something good to look at.